Hello everybody and welcome to my presentation. My name is Emma Chambers and I'm a postdoctoral researcher at the Dublin Institute for Advanced Studies. Today I would like to talk to you about using ambient noise tomography and seismicity to evaluate the importance of high temperatures and fluids within the Eastern Rift. And this was part of a placement project during my PhD, which was funded through the University of Southampton, where I was hosted at Tulane University by Cynthia Ebbinger. And in the background here we have the Oldonyo Lengai volcano, which is located in the Eastern Rift system, which I'll be talking about later. So the project had several aims, which included creating new shear velocity maps for the Northern Tanzania divergent zone, part of the Eastern Rift system. We wanted to do this at crustal depths using ambient noise and a purely seismic inversion. The interest for the region is the significant amount of magmatic activity, including dike intrusions in 2007 and 2008. Using this new model, we wanted to identify the depth at which melt is stored relative to recent seismicity studies in the region, and then compare back to the main Ethiopian rift, which is classified as being at a later stage of rifting due to age and the location of melt. By answering these questions, we can then determine what are the most important factors for determining the extent of rifting. So now to provide some background for the region. The Northern Tanzania divergent zone is within the Eastern Rift system and part of the much longer East African Rift system, which is located down through Africa, through here. It starts in the Afar region, progresses southerly down to Botswana and off to sides here and here in the south. The area has slow extension rates of about 1 to 5 millimeters per year, and there's less than 20% crustal extension. And the area we focus on is the Eastern Rift system in here, with Kenya to the north and Tanzania in the south. And the red box is the focus of our study. Magmatism in this region initiated at approximately 6 million years ago and has a very wide range of compositions. These include basalts, melolites, and carbonatites. The major faulting in the Natron Basin, so in this region in here, we've got border faults indicated by these black dashed lines here, has occurred since 3 million years ago. The crust is approximately 40 kilometers thick and it has been thinned to 29 kilometers thick beneath the Natron Basin, so thicker in this region and thinning to here. On the right, the red circles show recently located seismicity from Rice et al. 2021, and these are all focused within the rift and between key volcanoes, including the Oldonyo Lengai volcano here, which is a carbonatite volcano, and the Gelai volcano here, with seismicity also present in the Niger-Soito volcanic field. The seismicity also branches out southeast into the Manyara Basin, down here, and southwest to the Ngorongoro volcano and crater highland region. So for this study, we use the Crafty network, as shown by the purple triangles, which each is an individual seismometer, and this is located in Kenya and Tanzania. It was deployed from early 2013 to late 2014 and comprised of 39 three-component broadband seismometers. Due to timing issues, data from February to November 2013 was removed. The data was pre-processed and cross-correlated and resulted in 2,822 station pairs across the region between each station. The cross-correlations were then inverted for phase velocity, and we obtained results of periods from 6 to 17 seconds, or in terms of depth, upper crustal and mid-crustal depths. We only use the vertical components, resulting in a Rayleigh wave phase velocity maps for this region. We quickly look at the ray path coverage between the cross-correlated pairs. We can see that we have very good coverage for the full area at every period. We have great coverage in anywhere that we're going to study for all things, although they reduce with increasing period, but there is still coverage at all locations. The phase velocity dispersion curves between station pairs can then be inverted for a grid of nodes. So originally we had them between each station pair. We can then invert them to put them onto a grid for our entire location. These generate phase velocity maps, which are a factor of period, but can then be inverted again for shear velocity structure, which is a function of depth, with another inversion, which is a linear least squares inversion. We update an initial model, which is shown by the red line here, which is based on Raker et al. 2017. And we can see that we get a very similar average dispersion curves, though this varies across the region. And from our sensitivity kernels, we are sensitive to the upper and mid-crustal depths from about 5 to 22 kilometers depth. So you can see that from here, we've got peak sensitivity at 5 kilometers, and then remaining sensitivity kind of peters out at about 22 kilometers depth. So upper crustal and mid-crustal depths. So here we show the phase velocity results, and these give us an overview of velocity structure for the area with periods. Because we're using surface waves are dispersive. So at short periods, such as 6 seconds, we are sensitive to a shorter depth range, so kind of upper crustal depths, whereas at the longer periods, we're sensitive to a much wider range of depths. But we'll see that when we invert for shear velocity. But first of all, we find low velocities, which are shown by the red colors, such as here, within the crater highlands and the rift basins. We also find faster velocities, indicated by blue, at the border faults and at the rift margins. So kind of along this region and in here. So the off-rift sections. We also note that the Oldoño Lengo volcano, which is about here, which is an active carbonatic volcano, is slow at all periods within our study. If we invert for shear velocity, which is now a function of depth, so these are absolute depths, so you get an idea of exactly what range we're looking at. We see that low velocity zones are again in the crater highlands and into the rift zones, such as at 15 kilometers here. And we find that the slow velocity zones extend for about 8 to 19 kilometers depth within the rift. We overlay the recent seismicity study from Rice et al. 2021, which are shown by the yellow circles. They're plotted at plus or minus 2.5 kilometers depth, around the depth which is shown in the top left corner of each panel. The seismicity we find is located within or at the edges of all the low velocity zones and not present in the fast regions. They're also bounded by the border faults. We do not see the seismicity in here, and also we do not observe slow velocities outside the border faults. The seismicity also increases where the velocities get broader along the rift. So we should note that previous studies have looked into the composition of basalts, and we think that the slow velocity zones are regions where we have presence of melt, which has been interpreted by previous studies. The lavas in this area are a mix of basalts, melolites, and carbonatites, indicating that we have a deep, mid to lower crustal source for the melt in this region. The seismicity and velocities agree with this, with lower velocities and increased seismicity in the mid to lower crust, with little activity in the upper crust. The low velocities in the crater highlands, though, so at shallow depths of about 5 kilometers, are likely from unconsolidated sediments and ash, in contrast to the faster surrounding rocks, due to surface geology studies. So I said we were going to do a comparison to an area that's at a later stage of rifting. Now, the main Ethiopian rift is one such area and is located northeast of the Eastern Rift and is shown by the purple square here. It has similarities to the Northern Tanzania divergent zone, but it's thought to be at a more advanced stage of rifting. In the next slides, we'll zoom to this region, marked by the large red square, and compare the similarities and differences between the rifts of both regions. So for some context, in the Northern East African Rift, shown here, volcanism initiated approximately 45 million years ago, so it's a bit older than the previous region. The main flood basalt emplacement, shown by the blue polygon here, occurred about 31 to 29 million years ago. The area has variable crustal thicknesses, but within the main Ethiopian rift, which is shown by the red ring, where we'll focus our comparison, the crustal thicknesses vary between 25 to 35 kilometers thick, so a bit thinner than the previous region, which varies from about 29 to 40 kilometers thick. This area has undergone 20 to 30% crustal extension since rifting initiated. Remember, the past region was 20%. We use the same techniques described earlier to produce shear velocity maps of this region and compare to the northern Tanzania divergence zone. So previous work in the main Ethiopian rift by Chambers et al. 2021 also performed ambient noise tomography and found low velocities in the main Ethiopian rift region in here, so shown by the red square. But we should also note that they also find low velocities off rift. They're not just bounded by the rift and the border faults, which we did in the previous study. Two recent works use magnetotelluric methods and compositions to look at melt compositions and found an evolved magma system present at all crustal depths, including within the upper crust, so here and here, as shown in these two schematics by Hutchison et al. 2018 and Novaki et al. 2018. You see that the magmatic plumbing system is present at upper crustal depths, mid and lower crustal depths for both. And again, we have a lower crustal magma body, but we also have things above 5 kilometers depth in the surface. So when we compare the two regions, like I said, we find similarities and differences. The lowest velocities are within the rift, and seismicity focuses to the rift. They're also both locations with lots of melt. However, there are crucial differences. The lowest velocities in the eastern rift segment are more focused to the rift and are bound by the border faults, in contrast to the main Ethiopian rift, where low velocities extend significantly far off rift. Furthermore, while there is significant melt in both regions, the magma composition and depths are different. Within the main Ethiopian rift, melt is shallower and more evolved with para-alkaline lavas, and magma chambers are in the upper 5 kilometers and present at mid and lower crustal depths. It's quite an evolved magma system. In contrast, the eastern rift segment has compositions that indicate a deep source at mid to lower crustal depths. Finally, the deeper melts of the eastern rift section seem to have more gas present within them from previous studies, which has also been detected out at the border fault regions where we observe fast velocities, and these show up as a high velocity region. While fluids show up as a low velocity area, gas-rich regions seem to be imaged as a high velocity area. We can also plot these as two schematic cartoons, with the main Ethiopian rift on the left from a recent study by Chambers et al. 2021, where we see gradually shallowing melt bodies in the crustal depths shown by the disks through to the Afar region. In contrast to on the right with the Natron Tanzania divergence zone with the schematic from Rice et al. 2021, which did the seismicity zone, where we find that we have lower crustal and upper crustal melt bodies, lower crustal and mid crustal bodies, I should say, sorry, with little magmatism at the upper crustal depths, certainly not large magma chambers at the upper crustal depths. We observe a much more developed and full magmatic crustal system, including at shallow crustal depths within the main Ethiopian rift, more evolved melts, in contrast to the younger Natron Northern Tanzania divergence zone, which, while also having evolved melts, despite a younger age, has different compositional range of basalts, melolites, and carbonatites located at deeper depths than those of the main Ethiopian rift. So to conclude, we've produced a new shear velocity model at crustal depths within the Northern Tanzania divergence zone. We observed low velocities beneath the rift from about 10 to 18 kilometers depth, and these are likely due to melt in the region and are bounded by the border faults in the region. Seismicity maps well to the center and edges of our low velocity zones, which have also been interpreted as melt pathways. Combined with previous geochemical results, the magmas have a range of compositions in the eastern rift segment, suggesting a developed mid-crustal magmatic plumbing system from lower crustal to mid-crustal depths. When we compare this to the older in age main Ethiopian rift, we see similarities with low velocities in the rift, but the location of melt is shallower and extends beyond the narrow rift. Furthermore, despite less extension and crustal thinning, significantly evolved melt is present in the Eastern Rift, similarly to the main Ethiopian rift, suggesting the location and depth of melt during rifting is a more important rift control rather than the time and onset of rifting, as well as the amount of crustal thinning. So thank you for listening to my presentation, and please contact me with any questions that you might have on this work.